Okay, now we'll have a look at the reachability graph for symmetric net analysis. You've seen how to model a system using symmetric nets. You have seen a comprehensive, detailed example, and we'll build the reachability graph in order to perform analysis for the symmetric nets. The analysis is asking some questions like does the model conform to the specification, and the possibility to answer are to use different kind of systems like techniques like linear invariance, reduction theory, or constructing the reachability graph, and of course when the system is finite. We'll focus on this part here, and we'll try to take benefits from the structure of the model that is induced by the color functions, and we'll have different kinds of graphs later in the tutorial. Okay, so let's see the reachability graph construction algorithm and the most basic version of what we can do here. When we want to construct the reachability graph, we'll construct a graph starting from the initial state of the symmetric net, and then we'll explore all possibilities of firing and new states that are generated. So we'll have a graph with a set of states that will be rg.q here, and we'll have a set of arcs that will be rg.delta. So initially, and the initial part, the initialization is here. Initially, the set of states in the reachability graph only contains the initial state of the net, that is M0. There is no arc, we haven't done anything. The initial state of the reachability graph is M0, and there's only one state we know of that will be in this set states, which will be used to know which are the states to be processed during the execution of the algorithm. So, to start with, we only have M0. Then, as you can see, there is a loop here, so this white loop, that will construct the reachability graph. And we'll construct the reachability graph by exploring the states in this set of states, one by one, and while we still have states to explore, we'll repeat this loop. So we'll pick a state S in this set, and then remove it, because we'll handle it. So in the end, we don't need it anymore in the set of states to handle. And for each transition, and each possible color of the transition, if the transition is enabled with that color in that state, so that is the condition here. So that means I'm in a state, I have a transition T with a color C that I can phi. I will construct the state that is obtained by the firing, which is enhanced here. So S from S by transition T with color C, I get NS, new state. If this new state that is computed belongs already to the reachability graph, you don't have to add it because it's already there. Otherwise, it's not in the reachability graph, and that is this part. You add the new state here to set Q, and this new state has to be also handled afterwards by the generation. So it is added to the set of states that will be handled. And finally, something that you do in all cases, whether you add already this state or not, is this part, which consists in adding the arc that allowed you to generate the new state. So the arc from S to NS is added to the reachability graph, and it is labeled by the transition and the color that were used to obtain the new state. And so you repeat that as long as you have states to handle. Okay, so let's take the introductory example once again and generate the reachability graph of this small example. So here in this example we started with an initial marking that contains a black token in place resource here, and also all possible colors of color set C here in place idle. So you have idle processes that are named C1, C2, C3 that are waiting here, and they will eventually try to find T1 in order to be waiting for entering using a resource and then release the resource. So initially we have this initial marking M0 here. So initially, to construct the reachability graph, we construct M0. It contains the in place idle, the three colors C1, C2, C3, and the resource space is marked by one token. In this marking, you have three possibilities. All of them consist in firing T1. T1 is the only enabled transitions, since there is nothing in waiting and T2 is not enabled. There is nothing in busy, so T3 is not enabled. So you can try to find T1, and you can find T1 in three different manners. One of them is using token C1, one of them is using token C2, and the last one is using token C3. So if we go back to the reachability graph construction algorithm, you can see that you will have from that initial state three possibilities for this loop here. So you take the first one, so T1, C1, and you generate a new marking M1 here. This new marking is obtained by firing T1 with color C1. Therefore, you take C1 from place idle and you put C1 in place waiting here. And you can see that idle does contain only now C2 and C3, while waiting appears containing C1 and the resource has not been changed. The same applies to the other two marking here with M2 obtained by firing T1 with color C2, and the last one M3 obtained by firing T1 with color C3. And to build a reachability graph, we have to do the same, starting from M1, see which successors you can have, starting from M2, starting from M3, and so on. Okay. So to apply more advanced verification algorithms, we need a representation of the behavior of the system, and in our case we'll use the reachability graph. So we've seen how to build it. We have this crypto structure which is the reachability graph that we'll use for representing the behavior of the system. We'll have to model properties and to state properties that can be either state-based propositions, so propositions that express things on places, and it will be denoted by P of C to say it's true if the place P is marked by a color C. We have even-based proposition as well, so that will be denoted T of C to tell that transition T is enabled for color C. We'll represent the property to be checked using these propositions, but for example, we'll have reachability properties So that will state, for example, that for all states of the reachability graph, you have a certain property. So it could be expressed like P of C and not P of C1. So that will say place P contains token C, but doesn't contain token C1. So that is a way of expressing the properties. You could have another reachability property, such as for all states of the reachability graph, there exists a transition T and a color C, such that T can be defined with color C. And another way to express properties that we want to check on the model is also to have temporal properties, and in general two particular semantics that are admitted. So the linear time semantics that looks at an execution of the system in the Kruger structure, and the branching time semantics that looks at the execution of the system, but that is represented by an infinite tree. So now you've seen how to build a reachability graph, how you can use it for basic reachability analysis and for system analysis, but we'll see the two logics, LTL and CTL, in the next two sequences in order to express some properties and to have more properties to check.